My name is Qinglu Zeng. I'm a PhD candidate from KTH Royal Institute of Technology. I'm honored to be here and on behalf of Yangzhe to present our work. The topic is, do buildings really need comprehensive sensor networks, a graph theoretical framework for physical consistency modeling? At first, we want to thank the Sweden Energy Agency to support us. Then let's us move to our paper. The first is our motivation and challenges. Many building owners want to install new sensors to improve monitoring, visibility, and enable new services, such as HVAC system optimization. However, to do this needs high CAPEX, and it is complex. So we should reduce installations, especially in legacy systems. We think virtual sensing can help, but it needs massive manual labor and domain knowledge. And the building owners, especially small building owners, don't have the necessary resources and expertise. So how to solve that? We want to automatically configure the virtual sensing from the system topology through their physical consistency between the equipment and the sensors. So how can we identify virtual sensors? By leveraging the inherent physical consistency in the system. Before that, I want to explain three foundational concepts. The first is physical consistency. All the physical measurements are not isolated. They are governed by fundamental physical laws. The second is the physical redundancy. Since we have this kind of physical laws, if we measure sufficient variables, we can calculate the unknown variable by inverting the governing physical law. The third is the observability. It is the structural capacity to calculate the value of a state variable. Here is an example we used in our paper to demonstrate how our framework works in the real life. It is a balanced ventilation system with heat recovery from a typical office building in Stockholm. We have some assumptions. We only consider the temperature and mass flow rate sensors. We didn't consider the losses. Now let me briefly describe this system. We have 7 temperature sensors and 2 flow rate sensors, 2 physical components, the heat recovery and the heating battery. What we want to know is the mass flow rate here. So then, how to know that? Let's move to the methodology. It's about graph construction. This system can be mapped into this bipartite graph. It contains 10 variables, 2 components, and the relationships between them. Each component had its own governing equation. For the heat recovery, all the variables are known. So there exists analytical redundancy for fault detection. For the heating battery, only M3 is unknown. So there exists physical redundancy for solvable components. We can use the governing equation to calculate it. To make it readable for the computer, we construct an instance matrix. If the variable is involved in the component, then the value is 1. Otherwise, it is 0. So this graph can form this instance matrix, and only M3 is unknown. For the global variable set, it is the union of two mutually exclusive subsets, measured and unknown subsets. Then is about the unknown degree. We calculate it for each component at iteration k by this formula. If the unknown degree equals 1, then it is in the graph is in solvable condition. Only one unknown variable exists. We can use the governing equation to calculate it. If the unknown degree equals 0, it is in redundant condition. All the variables are null, so we can use it for the fault detection. If the unknown degree is greater than 1, it is in unsolvable condition. It contains multiple unknowns, so it remains unsolvable in this iteration. So when we want to know the answer of that question, so we conduct this observability propagation analysis. This is the system mapped by the system, the bipartite graph, and then it can form this instance matrix. Only M3 is unknown. So for the heat recovery, all the variables are known. So the unknown degree is 0. It is in redundant condition. For the heating battery, only M3 is unknown. So the unknown degree is 1. So it is in insoluble condition, and we can use the governing equation to calculate the M3. So how about the possible applications? In design phase, it can minimize CAPEX by optimizing the sensor placements. We use it, we can know which one is redundant, which one is necessary. In operation phase, it can conduct robust fault detection by cross-validation. In retrofitting phase, it can provide virtual sensors to avoid new installation and new wiring work. Of course, we need to acknowledge some limitations of our current stage. We didn't consider the uncertainties beyond theoretical physical laws. We need to identify sensors for safety reasons, such as the freeze protection. And the energy loss is simplified as constant value. In the future, we want to automate the modeling process with the existing semantic model. We also want to automate the components and the physical laws identification process. So in conclusion, to answer the research question, this framework has the physical consistency modeling. It abstracts the system into a bipartite graph and use the instance matrix to make it readable, machine readable, and then it has the virtual sensor identification. We conduct an observability propagation analysis using the unknown degree to achieve to identify the sensor redundancy. For the lifecycle engineering value, it can achieve the sensor network optimization and a robust fault detection in the design, operation, and retrofitting phase. That's all. Thank you.
Thank you.